In 2012, the world was told that the mystery of mass had finally been solved. Physicists at the largest machine ever built had found the Higgs boson, the particle the headlines called the God particle, and everywhere people said the same thing. The last missing piece of the puzzle had been found at last. But here is what almost nobody mentioned that summer. The Higgs boson was supposed to explain why things have mass, and yet, after its discovery, mass remained one of the deepest unsolved problems in all of physics. The proton that gives your body almost all of its weight gets nearly none of its mass from the Higgs field. The exact masses of every fundamental particle are still completely unexplained, and the Higgs boson itself has a mass that by our own best theory should not even be possible. The discovery was not a failure. It was a door, swinging open onto a mystery far larger than the one everyone thought had just been closed. Get comfortable. Hit subscribe if you're new here, because by the end of this, the weight in your own hand will feel like a stranger. Now, let's slowly ease into this. Part 1. The weight in your hand. Reach out right now and pick up the nearest object: a phone, a book, a cup of water, a pen. Hold it in your hand and feel its weight, that quiet downward pull toward the floor. That sensation is one of the most ordinary things you will ever experience, and it is also one of the deepest unsolved mysteries in all of physics. The pull you feel comes from mass. Mass is the property that makes matter feel like matter. It is the reason your feet press against the ground, the reason a loaded truck is harder to push than a bicycle, the reason stars collapse under their own weight, and planets manage to hold on to their atmospheres. Mass seems like the simplest, most obvious property in the universe. Everything you can touch has it. You have it. You have been experiencing mass every single second of your life. Gravity has been acting on your mass without pause, pulling you down, anchoring you to this spinning planet. You have never known a single instant without it, not once, not even for a heartbeat. It is so constant, so woven into ordinary life, that it feels less like a phenomenon to be explained, and more like a fact that simply is. And yet that ordinary, unremarkable weight in your hand is hiding something strange. Because for most of the 20th century, some of the most brilliant people who have ever lived could not explain where mass comes from, not in any deep sense. They could measure it. They could use it in their equations. They could predict exactly how an object of a given mass would move. But when they tried to build a fundamental theory of nature, a theory that explained how the smallest pieces of reality interact at the deepest level, mass turned into a wall they could not climb. In the year 2012, that wall seemed to come down. Physicists at the largest machine ever built announced that they had found a particle called the Higgs boson, and the world celebrated. Headlines everywhere declared that the mystery of mass had finally been solved. The missing piece of the puzzle, the last brick in our picture of the fundamental world, had been found at last. It was hailed as one of the greatest scientific achievements of the century, and in many ways it genuinely was. But here is what almost nobody talks about. The Higgs boson was supposed to explain why things have mass. And yet, after its discovery, mass remained one of the deepest unsolved problems in all of physics. I want to sit with that contradiction for a while tonight, because it is so much stranger and so much more beautiful than the headlines made it sound. The proton, the tiny particle that gives most of your body its weight, gets almost none of its mass from the Higgs field. The specific masses of every fundamental particle, the exact numbers, remain completely unexplained to this day. And the Higgs boson itself has a mass that, according to our very best theories, should not even be possible without an almost miraculous, razor-thin cancellation that no one can account for. The discovery in 2012 was not a failure. It was something far more interesting than a failure. It was a door a door that swung open and revealed, on the other side, a mystery even larger than the one everyone thought had just been closed. So tonight we are going to walk through that door together, slowly, and explore what is really on the other side. We are going to start with the simplest possible question, the one you could ask while holding that object in your hand. Where does its weight actually come from? And we are going to follow that question down, layer by layer, until the ground gives way beneath it. Along the way, you will meet a field that fills all of space, a particle that took half a century to find, a proton that is mostly made of nothing but energy, and a number so finely balanced that it looks like the universe is holding its breath. By the end, the weight in your hand will feel like a different thing entirely. For now, just keep holding it. Feel that pull. It is the most familiar sensation there is, and almost everything about why it exists is a question we still cannot fully answer. Let us begin at the moment physicists first realized they were in trouble. Part 2. The crisis nobody mentions. To understand why mass became a crisis, you first have to forget the picture of the world you were probably taught in school. Most of us carry around an image of atoms as tiny solar systems, little balls of electrons whirling around a tight clump of protons and neutrons, and we imagine that everything is built out of these miniature spheres bumping into one another. That picture is comforting, and it is also wrong. It is not even close to what physicists actually mean when they talk about the fundamental pieces of reality. The truth is stranger, and you need it to follow the rest of tonight's story. In modern physics, the most basic things in the universe are not particles at all. They are fields. A field is something that exists everywhere in space, at every single point, all the time. You are already familiar with some fields, even if you have never thought of them in quite this way. There is a gravitational field surrounding the Earth that tells objects which way to fall and how strongly. There is an electromagnetic field that fills the room you are in right now, carrying light and radio waves and the warmth of sunlight. When you see a rainbow, when you feel heat from a fire, you are experiencing a field in action. A field is not an object sitting somewhere. It is a property spread across all of space, a kind of invisible ocean that fills everything. Here is the idea that takes a moment to absorb. In the deepest theory we have, every type of particle corresponds to a field that fills the entire universe. There is an electron field stretching across the whole cosmos. There is an up quark field, a down quark field, a field for light itself. And each of these fields can be disturbed, can be made to vibrate, like the surface of a pond when you drop a stone into it. When one of these fields is excited in just the right way, that little knot of vibration is what we detect as a particle. An electron is not a tiny marble sitting in space. It is a ripple in the electron field, a localized trembling in something that spans the universe. A particle of light is a ripple in the electromagnetic field. Every particle you have ever heard of is a wave in its own underlying field. This framework is called quantum field theory, and it is the foundation of all modern particle physics. It is also the most precisely tested set of ideas in the history of science. Some of its predictions have been confirmed to better than 10 decimal places, an accuracy so extreme it is like measuring the distance across a continent and being correct down to the width of a human hair. Inside this framework, over the middle of the 20th century, physicists built a magnificent structure called the Standard Model. The Standard Model describes every fundamental particle we know of and 3 of the 4 fundamental forces of nature. There is the electromagnetic force, which governs light and holds atoms together. There is the strong nuclear force, which binds the smallest pieces of matter inside protons and neutrons. And there is the weak nuclear force, which governs certain kinds of radioactive decay and plays a quiet but essential role in how the sun produces its energy. The Standard Model is not a rough sketch. It is one of the most successful theories ever devised. Every particle it predicted has eventually been found. Its calculations match what experiments measure with staggering precision. If it were a bridge, it would be engineered to tolerances finer than the width of a single atom. But at the very heart of this beautiful structure there was a problem, and the problem was mass. In the 1960s and 70s, three physicists working toward the same insight, Sheldon Glashow, Abdus Salam, and Steven Weinberg, achieved something remarkable. They unified two of the forces. They showed that electromagnetism and the weak nuclear force, which look completely different in everyday life, are actually two faces of a single deeper force. Electromagnetism reaches across infinite distances. The weak force only operates across distances smaller than an atomic nucleus. They seem like total strangers. And yet, at very high energies, the kind that filled the universe in the first fraction of a second after the Big Bang, these two forces would have been indistinguishable, melted together into one. They called it the electroweak force, and it was one of the great intellectual achievements of the age. But this beautiful unification came with a price, and the price was strange. The particular mathematical machinery that made it work, a kind of framework called a gauge theory, demanded that the particles carrying the force be completely massless. Not light, not small, massless. Every force carrier in the theory had to have exactly zero mass, travelling forever at the speed of light with no inertia at all. And for one of them, this was fine. The photon, the particle of light that carries the electromagnetic force, really is massless. That part matched reality perfectly. But the particles that carry the weak force, called the W and Z bosons, are anything but massless. They are extraordinarily heavy. The W boson weighs in at about 80.4 giga-electron-volts. The Z boson is even heavier, around 91.2. To put that in human terms, these particles are roughly 85 to nearly 100 times heavier than a proton. They are among the heaviest fundamental particles known to exist. This was the crisis. The theory that so elegantly united two of nature's forces, a theory that was mathematically gorgeous and internally consistent, insisted that its force carriers weigh nothing. And reality stood there flatly contradicting it, holding up two of the heaviest particles in existence. Reality was saying one thing, and the most beautiful mathematics physicists had ever written was saying the exact opposite. You might think the obvious fix would be to simply write the masses into the equations by hand, to force them in and move on. But when physicists tried that, the entire structure collapsed. The theory began producing nonsense. It predicted probabilities greater than 100%, which is meaningless, like saying something is more than certain to happen. It generated infinities that could not be tamed or removed. Forcing mass into the equations did not patch the theory. It destroyed it. There is a deeper way to feel how radical this shift from balls to fields really is. When you imagine a particle as a tiny ball, you imagine an object with a definite location, a thing that is simply there, sitting in one spot, the way a marble sits in a bowl. But a field has no single location. It is everywhere at once. So when physicists say the electron is a ripple in the electron field, they are saying that the electron does not so much occupy a place as it represents a disturbance spread across a region, a knot of energy in something that has no edges and no center. Two electrons are not two separate objects in the way two marbles are. They are two ripples in the same universe-spanning field, two excitations of one underlying ocean. And that is part of why every electron in the cosmos is exactly, perfectly identical to every other. They are not copies. They are the same kind of disturbance in the same single field. Nothing in everyday experience prepares you for this, and yet it is the most precisely confirmed description of reality we possess. It is worth lingering, too, on just how thoroughly the Standard Model has been tested, because it shapes how seriously we should take the cracks we are about to find in it. This is not a tentative theory held together with hope. Some of its predictions have been checked against experiment and found correct to better than 1 part in a trillion. Quantities that the theory calculates from first principles match the measured values so closely that the agreement is like predicting the distance from one coast of a continent to the other and being right to within the thickness of a single hair. When a theory is that accurate, you do not lightly dismiss it. So when that same theory tells us something deeply uncomfortable, that it cannot explain the masses it describes, that one of its own particles should be impossibly heavy, we cannot wave the discomfort away by saying the theory is probably just wrong. The Standard Model has earned the right to be believed, even when it points at its own incompleteness. That is what makes the mystery of mass so serious. It is not the confusion of a bad theory. It is the honest admission of an extraordinarily good one. So physicists faced a genuine fork in the road. Either the beautiful electroweak unification was simply wrong, a mirage that happened to look elegant, or there was something else going on, some hidden mechanism, some unseen process that was secretly handing mass to these particles in a way that did not wreck the delicate mathematics. The answer, when it finally came, was one of the most ingenious ideas anyone has ever had about the physical world. It did not patch the theory, and it did not abandon it. Instead, it found a way to give particles mass while leaving the precious symmetry of the equations completely intact. To see how, we have to talk about what symmetry really means, and about a trick the universe seems to play, where a perfect symmetry can hide itself in plain sight. Part 3. Fields, not balls, and the symmetry that hides. Symmetry in physics means something deeper than 2 sides of a butterfly's wings looking alike. A symmetry is a transformation you can perform on a system that leaves the underlying physics unchanged. Rotate a perfect sphere by any angle, and it looks identical from every direction. That is rotational symmetry. Carry your physics experiment from one laboratory to another across the world, and the laws of nature work exactly the same way in both places. That is another kind of symmetry. Symmetry, in this sense, is about what stays the same when something changes, and physicists have learned over the last century that these hidden sameness rules are the secret architecture of reality. The deepest laws of nature are written in the language of symmetry. The electroweak theory rests on a particular and very demanding symmetry called gauge symmetry. This symmetry is not decoration. It is the load-bearing wall of the entire structure. It is what guarantees that the theory's calculations give finite, sensible answers, that probabilities add up correctly, that the mathematics behaves. Without gauge symmetry, everything falls apart into the same infinities and nonsense we talked about a moment ago. But here is the cruel catch at the center of the whole problem. In its pure, unbroken form, this gauge symmetry insists that the force carrying particles be massless. Writing a mass into the equations directly is like taking a perfect sphere and welding a heavy lump onto one side. The symmetry is broken, ruined, and all the beautiful mathematical properties that depended on it simply vanish. So physicists needed something that sounds almost impossible. They needed a way to give particles mass without destroying the symmetry. And the solution turned out to be one of the most subtle and elegant ideas in the history of thought. You do not destroy the symmetry, you hide it. This concept is called spontaneous symmetry breaking, and the idea is that the laws of physics can possess a perfect symmetry while the actual state the universe settles into does not display it. The symmetry is still there, fully present, written into the fundamental equations. But the real physical situation, the particular arrangement the world happens to fall into, does not reflect that symmetry on its surface. Let me give you the picture that physicists themselves use, because it makes the whole thing click. Imagine a ball balanced perfectly on the very top of a smooth, rounded hill. The hill is perfectly symmetric. Every direction down its slope looks exactly the same as every other. The ball sitting at the peak respects this symmetry completely. It is not leaning any particular way, not favoring any direction. But this situation is unstable, and you can feel in your gut that it cannot last. The ball will roll down, and the instant it begins to roll, it has to choose a direction. North, south, east, west, it picks one, and it comes to rest somewhere on the slope, in one specific spot, pointing one specific way. Now look at what happened. The hill itself never changed. It is still perfectly symmetric, every direction still identical to every other. The laws governing the ball, the shape of the landscape, are completely unchanged and completely symmetric. But the ball's final resting place breaks that symmetry. It sits in one particular location, even though no location was ever special. The symmetry did not disappear. It is still right there in the shape of the hill. It has simply gone into hiding, present in the rules, but invisible in the outcome. This is spontaneous symmetry breaking, and it is exactly what physicists believe happened to the universe. The Higgs field is the ball, and the universe is the hill. The laws of physics have the full, perfect electroweak gauge symmetry. But the Higgs field, instead of sitting quietly at zero like most fields do in their lowest energy state, rolled off the top of the hill in the early universe and settled into a non-zero value everywhere in space. It picked a value, the way the ball picked a direction, and that choice broke the symmetry, not by destroying it, but by hiding it. The equations still hold the full symmetry. The universe we actually live in just does not put it on display. This idea was worked out in the early 1960s by several groups of physicists, drawing on earlier insights from a physicist named Yoichiro Nambu about symmetry breaking in particle physics, and from Philip Anderson, who had seen something similar in the physics of superconductors, where symmetry breaking explains how some materials carry electric current with no resistance at all. So what does this Higgs field actually do, sitting at its non-zero value everywhere? Think of it as an invisible medium that fills all of space, a background presence woven into every cubic inch of the cosmos. Every particle moving through the universe is moving through this field, whether it notices or not, and certain particles interact with it strongly. The W and Z bosons, those troublesome heavy force carriers, interact with the Higgs field very strongly indeed. As they travel through space, they are constantly engaging with this background field, and that engagement slows them, resists their motion, gives them inertia. That resistance, that reluctance to be pushed around, is exactly what we mean by mass. The stronger a particle's interaction with the Higgs field, the more mass it carries. The weaker the interaction, the less mass. And the photon, the particle of light, does not interact with the Higgs field at all. It slips through completely unaffected, never feeling the field's presence, which is precisely why the photon remains forever massless and forever travelling at the speed of light. This same mechanism gives mass to the matter particles too, the electrons and quarks that make up everything you can touch. Each of them interacts with the Higgs field with its own particular strength, described by what physicists call a Yukawa coupling, named for the physicist Hideki Yukawa. The electron couples weakly, so it ends up light. The top quark couples more strongly than any other known particle, so it ends up as the heaviest fundamental particle we have ever found. And the beauty, the real genius of all this, is that it hands out mass without touching the sacred symmetry. The gauge symmetry is still there, still doing its essential job of keeping the mathematics consistent. It has just been hidden by the Higgs field's quiet, non-zero presence. The equations keep their perfect symmetry. The universe simply declines to show it to us. Let me invite you to stand at the top of that symmetric hill yourself for a moment, because feeling it from the inside makes the idea land in a way that no diagram can. Imagine you are standing at the very peak, and beside you rests a perfectly round ball, balanced on the highest point. Look around in every direction. The slope falls away from you identically, no matter which way you turn. North looks the same as south, east the same as west. There is no special direction, no preferred way to go. This is the symmetry, and you can feel it as a kind of perfect, poised indecision, a balance in which all directions are equal and none is chosen. The universe, in its earliest, hottest moments, was something like this: the Higgs field poised at the symmetric peak, no value chosen, all possibilities equal. But the peak is unstable, and you can feel that too, the slight wrongness of a thing balanced where it does not want to stay. The ball trembles, and then it rolls. It picks a direction, just one, and tumbles down the slope to rest somewhere on the side of the hill. The instant it does, the perfect symmetry you were standing in is gone from view. There is now a special direction, the one the ball happened to choose, even though no direction was ever truly special. Look back up at the hill itself, though. The hill has not changed at all. Every direction down its slope is still identical to every other. The symmetry is still there, in the shape of the landscape, in the laws that govern the ball. It has simply vanished from the situation, hidden inside a choice that had to be made. This is the strange and beautiful heart of it. The symmetry was never destroyed. It was only concealed, present in the rules, but invisible in the result. The early universe rolled off its peak, the Higgs field chose its value, and from that moment on, the perfect symmetry of the laws of physics has been hiding just out of sight, written into the equations, but absent from the world we see. Every particle that has mass, including the atoms that make up your body, owes its weight to that ancient, hidden choice. There is one more consequence of this idea, and it is the consequence that turned a piece of abstract mathematics into something you could actually go out and hunt for. If the Higgs field is real, if it truly fills all of space with a non-zero value, then it should be possible to create a ripple in it. Just as you can disturb the surface of a still pond and send a wave across it, you should be able to disturb the Higgs field by pouring enough energy into a small enough region, and that ripple, that excitation of the field, would show up to us as a particle. A brand new particle, the Higgs boson. I want to be very clear about something here, because it is the single most misunderstood point in this entire subject. The Higgs boson is not what gives other particles their mass. That is the Higgs field's job. The Higgs boson is a vibration in that field, a wave on its surface. It is the evidence that the field exists at all. Finding the Higgs boson would be like spotting a single wave rolling across the surface of an ocean you had long suspected was there, but could never see directly. The wave proves the ocean is real. And so, with a target finally in mind, the longest hunt in the history of physics began. Part 4. The 50-Year Hunt. The hunt for the Higgs boson lasted nearly half a century, and that long stretch of time is worth pausing on, because it tells you something about how science actually works at its frontier. The mechanism was proposed in 1964. The particle was not confirmed until 2012. That is 48 years, a span longer than many careers, longer than many lives in science. An idea was written down on paper, in equations, by a handful of theorists working from pure reasoning and physical intuition, and then the world had to spend nearly 5 decades and enormous resources building the machinery capable of testing whether that idea was true. Think about the faith and the patience that requires. A young physicist who believed in the Higgs mechanism in 1964 might have spent their entire working life waiting to find out if they were right. Part of what made the search so difficult is that the theory was frustratingly silent on one crucial detail. It predicted that the Higgs boson existed, but it did not predict what mass the Higgs boson should have. The physicists knew the particle was out there somewhere, but they did not know exactly where to look along the scale of possible masses. Imagine being told there is a single specific note hidden somewhere on a piano keyboard that stretches for miles, and you have to find it by playing every key. That was roughly the situation. The only way forward was to build machines powerful enough to search range after range of possible masses, ruling out regions one by one, slowly closing in. So that is what they did. Over decades, physicists built increasingly powerful particle accelerators, machines that smash particles together at higher and higher energies. The logic behind these machines is beautifully direct. To create a ripple in the Higgs field, you need to concentrate a great deal of energy into a tiny region of space. And the way you do that is to take particles, accelerate them to nearly the speed of light, and crash them into each other head-on. In the violence of that collision, the concentrated energy can momentarily excite the Higgs field and produce a Higgs boson, which then almost instantly decays into other particles that the detectors can catch. Experiments at CERN, the great laboratory near Geneva, and at Fermilab near Chicago, spent years narrowing the range of possible masses, eliminating the regions where the Higgs was not, steadily shrinking the territory where it could still be hiding. By the early 2000s, the search had closed in considerably, and a new machine was rising that would settle the question one way or the other. It would either find the Higgs boson or prove it did not exist in the range where it was expected to live. That machine was the Large Hadron Collider, and it is worth understanding just how extraordinary it is, because it represents one of the most ambitious things our species has ever built. The Large Hadron Collider sits inside a circular tunnel about 27 kilometers around, buried roughly 100 meters underground, straddling the border between Switzerland and France. Inside that ring, two beams of protons race in opposite directions, accelerated until they are moving at very nearly the speed of light, looping around the tunnel tens of thousands of times every second. When those two beams are steered into each other, the collisions release bursts of energy concentrated into spaces smaller than an atom, recreating, for the briefest possible instant, conditions that have not existed since a tiny fraction of a second after the Big Bang. Out of that energy, new particles can materialize, including, if the energy is high enough and you are patient enough to sift through trillions of collisions, a Higgs boson. The scale of this is hard to take in. Thousands of scientists and engineers from dozens of countries spent decades designing and building it. The detectors that watch the collisions, machines called Atlas and CMS, are themselves the size of buildings, packed with layer upon layer of instruments designed to track and identify the spray of particles that comes flying out of each collision. Humanity built a machine the size of a city, buried it underground, and used it to look for a single ripple in an invisible field that fills all of space. There is something almost unbearably hopeful about that, and it is worth holding on to that sense of scale and patience, because it sets up the emotional weight of what came next. For 48 years, an idea waited. Generations of physicists devoted themselves to a question they might never see answered. Billions of dollars and the coordinated effort of thousands of people across the world were poured into the search. All of it aimed at proving the existence of a particle that, if found, would confirm our explanation for why anything in the universe has mass at all. The stakes were not just technical, they were almost philosophical. Were we right about how the universe gives weight to its building blocks? Or had we, for half a century, been chasing a beautiful mathematical phantom? By the summer of 2012, after the machine had been running and the data had been piling up, the answer was finally about to arrive. And the people who had spent their lives on this question gathered in an auditorium at CERN to hear it. Part 5, July 4th, 2012. On the 4th of July, 2012, the auditorium at CERN was full. People had camped outside overnight to get a seat. The room held graduate students and senior physicists, some of whom had spent their entire careers working toward this single morning. Two teams were about to present their results, the Atlas team and the CMS team, working with separate detectors, separate methods, separate analyses, deliberately kept apart so that neither could influence the other. If both independent teams saw the same thing, in the same place, it would be very hard to dismiss as a fluke or an error. Picture the moment as the data goes up on the screen. The room is quiet in the particular way a room gets quiet when everyone in it understands exactly what they are looking at. On the plots, there is a bump. A small excess of events clustered at a particular energy, right around 125 giga-electron volts, exactly the kind of signature a Higgs boson would leave as it decayed. And it is there in both experiments at once, two independent teams pointing at the same spot from two different directions. The statistical significance is overwhelming. The probability that this bump is just random noise, a statistical accident, is less than 1 in 3 million for each experiment on its own. This is not a maybe. This is not a hint. This is a discovery, and everyone in that room knows it in the same instant. The particle predicted 48 years earlier, the ripple in the field that gives the universe its mass, has been found, sitting almost exactly where the theory said it should be. In the audience that morning sat Peter Higgs, then 83 years old, one of the physicists who had written down the idea back in 1964. He had spent nearly 5 decades carrying this prediction, and now, in real time, he was watching it become real. When the results were shown, he took off his glasses and wiped his eyes. He wept. A man in his 80s, watching an idea he had conceived as a young researcher, finally confirmed by a machine the size of a city, built by thousands of people, decades after he first put pen to paper. It is one of the most human moments in the history of science, an old man crying quietly in an auditorium because the universe had just told him he had been right all along. François Englert, who had independently developed the same mechanism with his colleague Robert Brout, was also there. But Robert Brout himself was not. He had died the year before, in 2011, just 1 year too soon to see the confirmation of the idea he had helped create. He missed it by a single year. The following year, in 2013, Higgs and Englert were awarded the Nobel Prize in Physics for the prediction. Brout, having passed away, could not share it because the prize is not awarded after death. I want you to sit with that scene for a moment because it carries the full weight of what science costs and what it gives back. 2 faces in one room, one man weeping because he lived to see it, and the empty space where another man should have been sitting, who did the same work and died 1 year short of the answer. That is the human texture of the search for mass. It was not just equations and machines. It was lives spent in patience and faith, some rewarded and some not, all bent toward a single question about why the universe has weight. And the discovery was, by every fair measure, a genuine triumph. It confirmed that the Higgs field is real. Not a mathematical trick, not a convenient fiction invented to patch up the equations, but an actual physical field permeating the entire universe, handing mass to the W and Z bosons and to the fundamental matter particles through their interactions with it. A mechanism proposed on paper in 1964, from nothing but reasoning and intuition, had been validated by experiment 48 years later. The electroweak theory, with its hidden symmetry and its clever Higgs mechanism, was correct. The Standard Model, the most detailed and precise theory of nature ever built, was at last complete. Every particle it predicted had now been observed. The world's headlines were not wrong to celebrate. This was one of the great confirmations of a theoretical prediction in the entire history of human thought. But here is where the story turns, and it turns in a direction almost nobody outside of physics noticed. Because confirming that the Higgs mechanism exists is not the same thing as explaining mass. It is not even close. And the discovery in that auditorium, for all its triumph, was not the closing of a book. It was a door opening onto a much larger and much darker room. The headline said the mystery of mass had been solved. The physics said something far more unsettling. The Higgs mechanism had answered one specific question, beautifully and completely. And in answering it, it had exposed at least 3 deeper questions that it could not touch at all. The first of those questions is so simple a child could ask it, and yet the most successful theory in the history of science has no answer to it whatsoever. Let us walk through that door now and see what is waiting. Part 6. The turn, where process is not pattern. The question is this: why does each particle have the specific mass it has? That is all. It sounds almost too simple to be a problem. The Higgs mechanism tells you how a particle gets its mass. A particle interacts with the Higgs field, and that interaction gives it mass. Fine. We understand the process, the machinery, the sequence of steps, but the mechanism is completely silent on a different and more obvious question. Why this much mass and not some other amount? Why is the electron as light as it is? Why is the top quark as heavy as it is? The Higgs mechanism does not say. It cannot say. And once you see this clearly, the celebrated solution starts to look like it explained far less than everyone claimed. Let me give you the actual numbers, because the numbers are where the strangeness lives. The electron has a mass of about 0.511 mega-electron volts in the units physicists use for these things. The muon is a particle that is, in almost every respect, simply a heavier copy of the electron. Same charge, same behavior, same way of interacting with the forces of nature. The only real difference is that the muon is heavier, and it is heavier by a very specific amount. It weighs about 207 times what the electron weighs. Then there is a third copy, called the tau, heavier still. The tau weighs about 3,477 times what the electron weighs. 3 particles that are essentially identical twins, except one is light, one is medium, and one is heavy, in a strange and very particular ratio. Now ask the obvious question. Why 207? Why not 200? Or 300? Or 50? Why is the tau roughly 17 times heavier than the muon instead of 10 times or 20? The standard model has no answer. None at all. The interaction strengths that determine these masses, those Yukawa couplings we talked about, are what physicists call free parameters. That phrase deserves to be understood plainly. A free parameter is a number that the theory does not predict and cannot predict. It is a number that physicists have to go out, measure in an experiment, and then plug into the equations by hand. The theory accepts whatever value you give it. It does not prefer one over another. It has no opinion about why the electron should be this light or the top quark that heavy. It simply says that whatever the coupling is, that determines the mass, and then it shrugs and waits for you to tell it what the coupling is. It is like discovering that a piano produces its sound through vibrating strings, understanding completely how string tension and length set the pitch, and yet being utterly unable to explain why someone tuned each string to the particular note it plays. You understand the mechanism perfectly. The physics of the vibrating string is no mystery, but the actual tuning, the specific choice of which string sings which note, is something the mechanism never touches. The machinery runs flawlessly, and nobody chose the settings, and nobody can say why the settings are what they are. And this is not some small gap around the edges of an otherwise complete theory. The masses of the fundamental particles span an absolutely enormous range. The lightest particles that have any mass at all, the ghostly neutrinos we will come to later, are at least 1,000,000 times lighter than the electron. The heaviest fundamental particle, the top quark, sits at about 173 giga-electron volts, which is roughly 340,000 times the mass of the electron. From the lightest to the heaviest, the masses cover at least 12 orders of magnitude, 12 factors of 10, a span so vast that if you scaled the lightest particle up to the size of a single grain of sand, The heaviest would be larger than a mountain. And across that entire staggering range, the Standard Model treats every single value as an arbitrary input. It looks at this 12 order of magnitude spread of masses and simply says, that is just how the universe happens to be. It offers no reason, no pattern, no underlying rule. It helps to see just how wild the pattern of these numbers really is, because the wildness is the whole point. Line up the 3 copies of the electron by their masses. The electron sits at the bottom. The muon is about 207 times heavier. The tau is about 3,477 times heavier than the electron. Now look for a pattern in those numbers, the way you would look for a rule in any sequence. Is each one 10 times the last? No. Is each 100 times the last? No. Do they follow some clean mathematical series, a doubling, a neat power, a familiar progression? They do not. The jumps are large and awkward and resist every simple description. Physicists have spent decades trying to fit these masses to formulas, to power laws, to elegant mathematical patterns, and the masses slip through every net. Some formulas look promising for 2 of the particles, and then fail completely on the 3rd. Others require so many adjustable knobs that they explain nothing at all, because a formula with enough free dials can be made to fit any numbers you like, which means it has no real predictive power. And the strangeness does not stop with the electron's heavy cousins. The same puzzle repeats among the quarks, only worse. There are 6 quarks, arranged in 3 pairs, and their masses sprawl across an even wider range. The lightest quarks weigh just a few mega-electron volts. The top quark weighs about 173,000 mega-electron volts. From the lightest quark to the heaviest, the masses span roughly 5 orders of magnitude, a factor of nearly 100,000, with no rhyme or reason anyone has been able to find. Why are there exactly 3 copies of each particle, 3 generations, and not 2, or 4, or 100? The Standard Model does not say. It happily accommodates 3, but it does not require 3. You could write down a perfectly consistent version of the theory with 2 generations, or with 7, and the mathematics would not complain. We know there are 3 because precise measurements at an earlier collider counted them, watching how a particle decayed and inferring that exactly 3 light neutrino types exist. But the number 3 is not derived from any principle. It is simply observed, written into reality for reasons no one can explain. This collection of unexplained numbers, the masses and the mixing patterns and the generation count, even has a name among physicists. They call it the flavor puzzle, and it has stood unsolved for half a century. It is the concrete numerical face of the deeper mystery, the place where why does this particle have this mass stops being abstract and becomes a specific list of stubborn numbers staring back at us, refusing to explain themselves. So, when people heard that the Higgs boson was discovered and that mass had been explained, this is the gap they did not hear about. The Higgs mechanism explains the process by which mass arises. It does not explain the pattern of masses we actually observe. It does not tell us why the universe chose this particular set of weights for its particles rather than some completely different set. It is the answer to how, with the question of why left entirely untouched. And if that were the only thing the Higgs left unexplained, it would already be a profound mystery. But it gets stranger, because it turns out that for most of the matter you have ever encountered, the Higgs mechanism is not even the main source of mass. It is barely a footnote. The weight of your own body comes overwhelmingly from somewhere else entirely, and to see where, we have to shrink down and go inside the proton. Part 7. Most of you is not the Higgs. Think about your own body for a moment, the weight of it, the way it presses into the chair or the bed beneath you right now. You can step on a scale and read that weight as a number. That mass is what keeps you anchored to the ground, what makes it take a little effort to rise from a chair, what gives you momentum when you walk. Now follow that weight downward into the structure of what you are made of. Your body is made of cells. The cells are made of molecules. The molecules are made of atoms. Each atom is a cloud of electrons surrounding a tiny, dense nucleus. The nucleus is made of protons and neutrons. And the protons and neutrons are made of quarks, bound together by particles called gluons. We have reached the bottom, or nearly so. Almost all of your weight lives in those protons and neutrons, in the nuclei at the hearts of your atoms. Here is the fact that should genuinely stop you in your tracks. The quarks inside a proton, the up quarks and down quarks that make up nearly all the visible matter in the universe, are extraordinarily light. An up quark has a mass of roughly 2.2 mega-electron volts. A down quark has a mass of roughly 4.7 mega-electron volts. A proton is made of 2 up quarks and 1 down quark, so add them up. 2 up quarks and 1 down quark come to about 9.1 mega-electron volts of quark mass total. But the actual measured mass of a proton is about 938.3 mega-electron volts. Look at those two numbers side by side. The quarks inside the proton account for about 9 of its 938 units of mass. That is less than 2%. The quarks contribute less than 2% of the proton's mass. The other 98% comes from somewhere else entirely. Not from the Higgs field, not from the mass of the quarks themselves. It comes from energy. This is one of the most remarkable facts in all of physics, and almost nobody outside the field has ever heard it. The mass of nearly everything you have ever touched, every mountain, every ocean, every person you have ever loved, comes overwhelmingly not from the Higgs mechanism, but from the energy of the strong nuclear force binding quarks together inside protons and neutrons. To understand how energy becomes weight, you have to understand something genuinely strange about the strong force. The strong force is carried by particles called gluons. Gluons, like the photon, are massless, but unlike the photon, gluons interact with each other. The photon carries the electromagnetic force, but does not itself carry electric charge, so photons ignore one another completely. Gluons carry a kind of charge of their own, called color charge, and because they carry it, they pull and push on each other, tangling together in ways that make the strong force behave like nothing else in nature. The strangest property of the strong force is called confinement. Quarks are never, ever found alone. You cannot isolate a single quark. No one has ever held one by itself, and no one ever will. Whenever you try to pull two quarks apart, the force between them gets stronger, not weaker. This is the opposite of everything your intuition expects. Gravity weakens as objects move apart. The electric force weakens as charges separate. But the strong force grows as quarks try to escape one another, like a rubber band that pulls back harder the farther you stretch it. And if you pull hard enough on a real rubber band, eventually it snaps. When the strong force field between two quarks is stretched far enough, something extraordinary happens instead of snapping into freedom. The energy stored in that stretched field becomes so enormous that it converts directly into new matter, conjuring fresh quarks and antiquarks out of pure energy. The quarks you were trying to separate immediately grab these new partners and bind into new particles. You set out to free a single quark, and you end up creating several new particles instead. The quark stays confined. It always stays confined. Now I want to take you inside a single proton, because the picture there is nothing like the tidy diagram of 3 little balls you might imagine. Shrink down with me, smaller and smaller, past the scale of atoms, past the nucleus, until a single proton fills your view. What you find is not calm. It is a churning, roiling storm of activity, a furnace of energy packed into a space about 1/4,000,000th of a meter across. The 3 quarks that give the proton its identity are not sitting still. They are confined to such an unimaginably tiny space that the laws of quantum mechanics force them to carry enormous momentum, and so they tear around inside their cage at a significant fraction of the speed of light, never resting. Between them, gluons fly back and forth without pause, carrying the strong force, and because gluons spawn more gluons, the space fills with them. And because the energy crammed into this region is so intense, pairs of quarks and antiquarks are constantly flashing into existence out of the vacuum, living for the briefest flicker of time, and then annihilating back into nothing. The interior of a proton is a seething quantum soup. 3 real quarks adrift in a boiling sea of gluons and fleeting particle pairs, all of it crackling with energy. And every bit of that energy, by Einstein's most famous equation, the relationship that energy and mass are 2 faces of a single coin, every bit of that churning energy is weight. That is where your mass comes from, not from stuff, from motion and force, and the bottled energy of a storm too small to see. Physicists have confirmed this picture through a heroic kind of calculation called lattice QCD. The idea is simple to state and brutal to carry out. You take the equations of the strong force, lay down a grid of points across a tiny region of space and time, and then use the world's most powerful supercomputers to calculate how the quarks and gluons behave on that grid, summing over a staggering number of possible configurations. A single such calculation of the proton's mass can devour millions of hours of supercomputer time, and the result is breathtaking. Starting from almost nothing, just the tiny masses of the quarks and the strength of the strong force, lattice QCD reproduces the measured mass of the proton. When physicists break that mass down into its sources, they find the energy of the quark's motion, the energy stored in the gluon field, and a subtle quantum effect, all contributing the overwhelming majority, with the actual quark masses contributing only a small sliver, well under 10%. The proton's weight is conjured almost entirely out of energy and motion and force. It is one of the most dramatic examples of emergence anywhere in physics, a property that does not really exist in the individual pieces somehow blazing into being in the whole. I want to slow down inside the proton even further, because the more closely you look, the more astonishing it becomes. Hold in your mind that the 3 quarks said to make up a proton are not really the whole story, not even close. Physicists call those 3 the valence quarks, the ones that give the proton its identity, 2 up and 1 down. But they drift inside a churning sea. The intense energy crammed into that tiny space is constantly boiling, and out of that boiling, pairs of quarks and antiquarks flash into existence and wink back out, over and over, faster than any clock could mark. These are called C-quarks, and at any given instant, the inside of a proton holds not 3 quarks, but a fluctuating crowd of them, plus a swarm of gluons, all of it appearing and vanishing, a population that has no fixed number, because it is being created and destroyed continuously by the raw energy of the strong force. When you weigh a proton, you are weighing this entire seething crowd, this whole storm, not 3 tidy particles. Consider the gluon field itself, separate from the quarks. In most of physics, a force field weakens smoothly as you move away from its source. The gravitational field of a star fades with distance. The electric field of a charge falls off as you pull away. But the color force field between quarks does the opposite. Try to stretch it, and it stores more and more energy the further you pull. Like a spring that grows stiffer, the more you extend it, never relaxing, never giving up. This field is among the most intense in all of nature, and it is not a passive backdrop against which the quarks move. It is an active, energetic medium in its own right, and it contributes a large share of what your bathroom scale reads in the morning. Then add the motion of the quarks. Confined to a space about 1/4 of a meter across, the laws of quantum mechanics forbid them to sit still. The tighter you box a quantum particle, the more violently it must move, and so the quarks tear around inside their cage at speeds approaching that of light, carrying enormous energy of motion. All of it, the boiling sea, the stiff and storing field, the frantic confined motion, all of it is energy, and all of that energy is weight. When physicists run their great lattice calculations to confirm this picture, breaking the proton's mass down into its sources, the result is almost poetic. They find that the energy of the quark's motion contributes a large portion, roughly a third. The energy stored in the gluon field contributes another large portion, more than a third. A subtle quantum effect tied to the way the strong force behaves contributes a further substantial slice. And the actual masses of the quarks, the only part that comes from the Higgs field at all, contribute under a tenth, a thin sliver at the bottom of the ledger. Put it all together, and the proton, the thing that gives your body almost all of its weight, is revealed to be a furnace of bottled energy wearing the disguise of a solid particle. You are not, at the deepest level, made of stuff in the way you imagine. You are made of trapped motion and frozen force, and the small remainder that the celebrated Higgs mechanism provides would barely register on any scale at all. So, here is where we have arrived, and I want to let it land fully. When you step on a scale in the morning, you are not mostly weighing matter. You are weighing energy. The number on the scale is, overwhelmingly, the bottled-up energy of the strong force seething inside every proton and neutron in your body, converted into weight by the equivalence of energy and mass. You are, in the most literal physical sense the universe allows, far more motion and force held in place than you are solid substance. And the Higgs mechanism, the great celebrated triumph that won Nobel Prizes and filled the world's headlines with the news that mass had been explained, is responsible for less than 2% of you. The discovery that the world was told had solved the mystery of mass turns out to barely touch the mass you carry around every day. The weight in your hand, the weight of your own body, is almost entirely something else, something stranger, something the headlines never mentioned, and we are still not at the deepest layer of the mystery. Because the Higgs boson, the particle itself, has a problem of its own, and it may be the most disturbing problem in all of theoretical physics. Part 8. The particle that should not be this light. The Higgs boson was discovered with a mass of about 125 giga-electron volts. That number has since been measured with extraordinary care by both experiments at the Large Hadron Collider, refined over years of additional data to a value near 125.1 giga-electron volts, known now to better than 0.1%. It is one of the most precisely measured quantities in all of particle physics. And here is the problem, the one that keeps theoretical physicists up at night. According to the Standard Model's own mathematics, that mass should not be 125 giga-electron volts. It should be enormously, catastrophically, almost unimaginably larger. And the fact that it is not requires either an explanation we simply do not have, or a coincidence so extreme that it strains the meaning of the word. To see why, you need one more idea about how quantum mechanics shapes the properties of particles. In quantum field theory, nothing exists in isolation. Every particle is in constant conversation with every other particle and with the restless quantum vacuum itself. Even in what we think of as perfectly empty space, the quantum fields are never truly still. They flicker and fluctuate, and virtual particles pop into existence and vanish again, borrowing energy from the vacuum for the briefest of moments before paying it back. These are not science fiction. Their effects have been measured in the laboratory with great precision. They are as real as anything you can hold. And these constant quantum fluctuations affect the properties of every particle, including the mass of the Higgs boson. In quantum field theory, a particle's mass is not simply a number written into the equations once and left alone. It receives contributions from every virtual particle that interacts with it. Every particle that couples to the Higgs field nudges the Higgs boson's mass up or down with its own quantum correction. For most particles, these corrections are small and well-behaved, easily calculated and accounted for. But the Higgs boson is different in a way that turns out to be disastrous. The Higgs boson is a scalar particle, which means it has zero spin, no intrinsic sense of rotation or direction. And the way quantum corrections work for scalar particles is fundamentally different from how they work for particles that have spin. For particles with spin, like electrons or the W boson, certain symmetries stand guard over their masses, ensuring that the quantum corrections stay proportional to the particle's own mass. So if the particle starts out light, the corrections stay small and the mass stays light. There is a protective mechanism built into nature for them. The Higgs boson has no such protection. Nothing in the known laws of physics shields a scalar particle's mass from receiving truly enormous corrections. Corrections proportional not to the particle's own modest mass, but to the very highest energy scale that exists in the theory. And in the standard model, the highest energy scale is the Planck scale, the energy at which gravity itself becomes as strong as the other forces and our current physics breaks down entirely. The Planck scale sits at roughly 10 to the 18th power giga-electron volts. That is an incomprehensibly large number, about 10,000 trillion times the energy at which the Higgs boson was actually discovered. When you sit down and calculate the quantum corrections to the Higgs boson's mass in the standard model, including the contributions from all those virtual particles all the way up to the Planck scale, the answer that comes out is staggering. The corrections do not nudge the mass a little. They hurl it almost all the way up to the Planck scale itself. The natural value, the mass you would expect if you just let the mathematics run free without any interference, is a Higgs boson roughly 10 to the 16th power times heavier than the one we actually measure, 16 orders of magnitude. The predicted mass and the observed mass differ by a factor of 10,000 trillion. This is the hierarchy problem, and it is one of the most famous and most troubling puzzles in all of theoretical physics. The question it poses is brutally simple. Why is the Higgs boson so light? Now, you might reasonably guess at an answer. Maybe the enormous quantum corrections just cancel out. Maybe some contributions push the mass up, while others push it down, and they nearly cancel, leaving behind the small value we see. And in fact, that is technically what must be happening in the standard model. The bare mass of the Higgs, the raw number written into the fundamental equations before the quantum corrections are added, must be chosen with almost unbelievable precision, so that when you add in all those colossal corrections, the leftover is exactly 125 giga-electron volts. The bare mass must cancel against the quantum corrections to a precision of roughly 1 part in 10 to the 32nd power, and depending on exactly where you place the cutoff, perhaps even 1 part in 10 to the 34th. Let me try to make that number real, because it is almost impossible to feel its size. Imagine you are balancing a bank account. The account receives deposits and withdrawals from many different sources. Some deposits are enormous, billions of dollars. Some withdrawals are equally enormous, also billions of dollars. Each individual transaction is colossal, but when you add them all up at the end, the final balance must come out to exactly $125.37, not $125.38, not $125.36, exactly $125.37. If any single transaction among those billions were off by even the tiniest amount, the final balance would be wildly wrong, billions of dollars instead of 100 and change. That is the hierarchy problem. The quantum corrections to the Higgs mass are those enormous deposits and withdrawals, each one 10 to the 16th power times larger than the final answer, and somehow They must cancel with such perfect precision that the leftover is the tiny mass we observe. And nothing in the standard model enforces this cancellation. There is no rule that makes it happen. It simply has to come out right, digit after digit, for 32 or more decimal places. There is a way physicists describe this sensitivity that captures just how exposed the Higgs boson is, and it is worth understanding. They say the Higgs mass is ultraviolet sensitive. The word ultraviolet here has nothing to do with the kind of light that gives you a sunburn. In the language of physics, it is shorthand for high energy, for the very smallest distances and the very largest energy scales. To say the Higgs mass is ultraviolet sensitive is to say that it feels the influence of whatever physics exists at the highest energies, even energies far beyond anything we could ever hope to probe directly. Whatever happens at the Planck scale, whatever happens at the grand unification scale, whatever new particles or forces might live up there in the unreachable heights of energy, all of it feeds directly into the mass of the Higgs boson. The Higgs is like an antenna with no filter, picking up signals from every energy scale in the universe at once and summing them all into a single number, its own mass. For that sum to come out to the modest 125 we measure, rather than something near the Planck scale, requires either a profound and hidden explanation or a coincidence that beggars belief. Compare this to a particle that is naturally light, and the contrast makes the problem vivid. Take the electron. The electron is also light, far lighter than the Planck scale, and yet nobody loses sleep over the electron's mass. Why? Because the electron is protected. There is a symmetry in the theory, a particular mathematical property that guards the electron's mass and keeps the quantum corrections to it small and proportional to the mass itself. If the electron's mass was zero, that symmetry would become exact, and physicists have a principle articulated decades ago that a small number is natural precisely when setting it to zero would increase the symmetry of the theory. By that standard, the electron's smallness is natural. There is a reason for it, a guardian built into the laws, but the Higgs boson has no such guardian. Setting the Higgs mass to zero does not increase the symmetry of the theory in any known way. There is no protective principle, no symmetry standing watch, nothing in the standard model that makes a small Higgs mass natural. The electron is light for a reason. The Higgs, as far as we can tell, is light for no reason at all, and that absence of a reason, in a quantity balanced to 32 decimal places, is what physicists find almost unbearable. It is the difference between finding a pencil lying flat on a table, which needs no explanation, and finding one balanced upright on its point, which demands one. Stand for a moment at this cosmic ledger and watch it happen. Imagine the corrections pouring in from every energy scale in the universe, signals from the Planck scale, from the grand unification scale, from everywhere, each one vast beyond comprehension, pushing the Higgs mass up and pulling it back down by amounts 16 orders of magnitude larger than the result. And watch them settle, against all odds, into the modest little value of 125. It is like watching a hurricane's worth of forces conspire to balance a single pencil perfectly upright on its sharpened tip. Physicists call this discomfort the problem of naturalness. A pencil standing on its point is not forbidden by the laws of physics. It is perfectly allowed. But if you walked into a room and found one standing there, balanced and motionless, you would not shrug and call it luck. You would look for a hand, a wire, a mechanism, something holding it up. The expectation that a fundamental theory should not require an absurd, unexplained fine-tuning is what physicists mean by naturalness, and by that standard, the Higgs mass is the least natural number in all of physics. The particle the world celebrated as the final piece of the puzzle turns out to carry the deepest crack in the entire theory. Its mass is the number that makes the least sense. And for decades, physicists thought they knew what was holding the pencil up. They had a beautiful answer ready. The only problem is that when they finally went looking for it, it was not there. Part 9. The answer that never came. For decades before the Higgs boson was even found, physicists were already worried about the hierarchy problem, already troubled by the question of why the Higgs mass should be so impossibly light. And they had developed a solution they found deeply, almost irresistibly beautiful. It was called supersymmetry, often shortened to SUSY, and for a generation of physicists, it was not merely a hypothesis. It was a way of seeing the universe, a framework so elegant that many were certain it had to be true. Supersymmetry proposes that every known particle has a heavier partner particle, a twin with different spin properties. For every matter particle, there would be a partner force carrier type particle. For every force carrier, there would be a partner matter type particle. The electron would have a partner. The quarks would have partners. The photon would have a partner. The Higgs boson would have a partner. A whole shadow family of particles, a mirror set of the entire particle zoo, waiting to be discovered. And the reason physicists loved it was not just its symmetry and elegance. It was that supersymmetry solved the hierarchy problem in the most satisfying way imaginable. Remember those enormous quantum corrections that push the Higgs mass toward the Planck scale, the ones that have to cancel with absurd precision? In a supersymmetric universe, that cancellation is not a coincidence at all. It is guaranteed. The contributions from the ordinary particles push the Higgs mass in one direction, and the contributions from their supersymmetric partners push it in exactly the opposite direction, with precisely the right size to cancel them out. The enormous corrections subtract themselves away automatically, naturally, leaving a small Higgs mass with no fine-tuning required at all. The pencil is no longer balancing by miracle. Supersymmetry is the hand holding it up, and supersymmetry offered even more. It naturally provided a candidate for dark matter, the mysterious, invisible substance that makes up about a quarter of all the energy in the universe and whose nature remains unknown. The lightest supersymmetric particle, if it were stable, would have just about the right properties to be that dark matter. Supersymmetry also improved the way the forces of nature unify. In the plane standard model, the strengths of the three forces come close to meeting at very high energies, but just barely miss. Add supersymmetry, and they converge to a single point with beautiful precision, hinting at a deeper unification waiting above. For all these reasons, supersymmetry became the dominant idea in theoretical particle physics for decades. Thousands upon thousands of papers were written about it. Entire careers were built on working out its consequences. Graduate students were trained in its mathematics. When the Large Hadron Collider was being designed and built, one of its primary goals, one of the things it was specifically engineered to find, was supersymmetric particles. Many physicists were not just hopeful, they were confident. Some considered the discovery all but inevitable, a matter of turning on the machine and waiting. The machine turned on. It has been running since 2010. The two great detectors, ATLAS and CMS, have analyzed trillions upon trillions of proton collisions at the highest energies ever produced in a laboratory, and they searched for supersymmetry in every way anyone could devise. They looked for the partner particles under dozens of different names, in dozens of different decay channels, using hundreds of different analysis techniques, sifting through datasets of unprecedented size and quality. Picture the control rooms over those years. Run after run, collision after collision, the detectors firing, the data flooding in, the analyses grinding through it, and the results came back, again and again, the same. The plots matched the predictions of the plane standard model exactly. No partner particles, no excess events where supersymmetry said there should be some, no unexpected bumps in the data, no missing energy signatures that could not be explained by ordinary, known physics. Just the standard model, working perfectly, with nothing extra. Year after year, Run after run. The answer was the same: quiet, devastating nothing. There is something heavy about that kind of silence, and it is worth feeling rather than rushing past. Imagine spending 20 or 30 years of your life calculating the precise predictions of supersymmetry, building your scientific identity around the conviction that these partner particles were real and waiting just above the energies the previous machines could reach. And then imagine the most powerful machine ever built, switching on, looking exactly where you said to look, and finding empty space. The limits crept upward year after year. The masses where the partner particles could possibly be hiding were pushed higher and higher. For many types of these particles, the searches now tell us that if supersymmetric partners exist at all, they must be heavier than about 2000 giga-electron volts, and for some, heavier still. And here is the cruel twist. If the partners are that heavy, supersymmetry no longer solves the problem it was invented to solve. The whole point was that the partners would cancel the quantum corrections cleanly. But if they are very heavy, the cancellation is no longer exact, and you are back to needing fine-tuning, perhaps not as extreme as before, but still uncomfortable, still unexplained. The beautiful solution, dragged up to high enough masses to survive the experiments, stops being beautiful. It is worth pausing to feel the strangeness of a scientific result that is, in essence, an absence. We are used to discoveries being something appearing where there was nothing, a new particle showing up in the data, a new signal rising out of the noise. But the absence of supersymmetry at the Large Hadron Collider is a discovery of the opposite kind. It is the profound significance of nothing appearing where something was confidently expected. Picture the data as it accumulates over the years, the plots filling in collision by collision. Theorists had drawn, in advance, exactly what the footprints of supersymmetry would look like, the telltale bumps, the missing energy carried off by invisible partner particles, the cascades of decays. Everyone knew the shape of the expected signal, and as the real data poured in, it settled, again and again, onto the smooth curve of the plain standard model, with the expected supersymmetric bumps simply not there. The footprints never appeared. The snow stayed unbroken. In a control room somewhere beneath the border of France and Switzerland, the most anticipated guest in the history of particle physics simply never arrived, and after years of waiting, the physicists had to confront that the chair they had set out was going to stay empty. This absence has forced some of the deepest souls in physics to question assumptions they had held for their entire careers. The principle of naturalness, the very intuition that told us the Higgs mass should not be so finely tuned that the universe should not balance pencils on their points without a reason, is itself now under suspicion. What if naturalness was never a law of nature at all, but only a human preference, an aesthetic, a hope that the universe would be tidy in the way we find satisfying? Perhaps the cosmos really is fine-tuned. Perhaps the Higgs mass really is a number balanced on a knife's edge for no deeper reason, and our discomfort with that says more about us than about reality. This is a genuinely unsettling possibility, because naturalness has been one of the most productive guiding ideas in physics for half a century, leading again and again to real discoveries. To give it up would be to lose a trusted compass. And yet, experiment after experiment has come back empty, and a trusted compass that keeps pointing at empty rooms eventually has to be questioned. Some physicists now wonder whether the apparent fine-tuning of the Higgs is explained not by any mechanism at all, but by a kind of cosmic selection, the idea that the Higgs mass takes different values in different vast regions of a much larger reality, and that we find ourselves in a region where it happens to be small simply because only such regions can contain atoms and stars and observers capable of asking the question in the first place. Whether that is a real explanation or an admission of defeat is one of the most heated arguments in physics today, and it is far from settled. The emotional impact of this on the physics community is genuinely hard to overstate. For decades, supersymmetry had been more than an idea. It was a worldview, a near certainty, the expected next chapter of physics, and the universe simply declined to confirm it. This forced a real reckoning. Some physicists remain committed, arguing the partners may just be heavier than we hoped, lurking somewhere beyond the energies we can currently reach, waiting for a bigger machine. Others have begun to question whether naturalness itself, the whole intuition that the universe should not be fine-tuned, was ever a reliable guide. Perhaps, they say, the universe really is fine-tuned, and our discomfort with that reflects a human prejudice rather than a law of nature. Still others have turned to entirely different ideas, frameworks that lived for years in supersymmetry's shadow. Composite Higgs models, in which the Higgs boson is not a fundamental particle at all, but a bound state of smaller pieces, the way a proton is built from quarks. Models with extra dimensions of space, models in which the Higgs mass was set by a slow cosmic process in the early universe. These ideas are creative and motivated, and so far not one of them has produced a confirmed experimental signature either. The absence of supersymmetry at the Large Hadron Collider stands as one of the most significant experimental results in recent physics, and it is a result written entirely in the negative. The leading answer to the deepest problem in the theory was searched for with the greatest machine ever built, and it did not appear. The pencil is still standing on its tip, and we no longer know what is holding it up. Part 10. Ghosts with Mass. There is a third great mystery of mass, and it concerns the strangest particles in the entire Standard Model. They are called neutrinos, and right now, as you listen to this, roughly 100 trillion of them are passing through your body every second. They stream out of the sun in unimaginable numbers, pour through the Earth as if it were not there, and slip through you without disturbing a single atom. They interact with matter so weakly that a neutrino could pass through a wall of solid lead, light years thick, and most likely emerge on the other side untouched. They are the closest thing the universe has to ghosts. And for decades, the Standard Model said these ghosts had no mass at all. This was not a guess or an approximation. It was built into the structure of the theory. The original Standard Model contained no mechanism whatsoever for giving neutrinos mass. They were taken to be exactly massless, travelling at the speed of light, weightless. And for a long time, this seemed perfectly fine, because neutrinos are so fiendishly difficult to detect that measuring their properties at all is a monumental challenge. But in the late 1990s and the early 2000s, a series of experiments delivered a result that shook particle physics to its foundations. Neutrinos have mass. They are not massless after all. And the way physicists discovered this is one of the most beautiful detective stories in modern science. There are 3 types, or flavors, of neutrino. There is the electron neutrino, the muon neutrino, and the tau neutrino, each one paired with its corresponding heavier cousin among the charged particles. When a nuclear reaction in the heart of the Sun produces a neutrino, it produces an electron neutrino, specifically. The flavors are distinct, well-defined identities, but quantum mechanics permits something deeply peculiar. If neutrinos have mass, and if their mass states do not line up perfectly with their flavor states, then a neutrino born as one flavor can transform into another as it travels through space. An electron neutrino created in the core of the Sun can arrive at the Earth as a muon neutrino or a tau neutrino, having quietly changed its identity somewhere along the 8-minute journey across the void. This shape-shifting is called neutrino oscillation, and the crucial point is this: oscillation can only happen if neutrinos have mass. If they were truly massless, the transformation would be mathematically forbidden. So when physicists observed neutrinos changing flavor, they had caught the universe red-handed. The oscillation itself was direct, undeniable proof that neutrinos carry mass. The evidence came from deep underground. The Super Kamiokande experiment in Japan, a vast cavern holding 50,000 tons of ultra-pure water watched by thousands of light sensors, observed neutrinos created in the upper atmosphere, oscillating between flavors as they passed through the Earth. And the Sudbury Neutrino Observatory in Canada, buried deep in a mine, solved a mystery that had puzzled physicists for decades, the so-called solar neutrino problem. For years, detectors had been catching only about a third of the electron neutrinos the Sun should be producing. Where were the rest? The Sudbury Observatory showed that they had not vanished at all. They had simply changed flavor on the way, transforming into muon and tau neutrinos that the older detectors could not see. When you counted all three flavors, the numbers matched the predictions perfectly. The neutrinos were never missing, they were in disguise. For these discoveries, Takaaki Kajita and Arthur MacDonald shared the Nobel Prize in Physics in 2015 for proving, beyond any doubt, that neutrinos have mass. And this is where neutrinos become a genuine crisis for the Standard Model, because the theory in its original form had no way to give them mass. To understand why, you need to know that particles come in left-handed and right-handed varieties, a property related to how a particle's spin lines up with its motion. The ordinary mechanism that gives a particle its mass through the Higgs field works by connecting the left-handed version of a particle to the right-handed version. Both versions have to exist for the mechanism to work. For the electron, this is fine because both left-handed and right-handed electrons exist, and the Higgs field links them together. But the original Standard Model contained only left-handed neutrinos. There were no right-handed neutrinos in the theory at all, and without a right-handed partner, there is nothing for the Higgs field to connect the left-handed neutrino to. The standard mechanism simply cannot function. The neutrinos should be massless, and yet they are not. So how do neutrinos get their mass? This is one of the biggest open questions in all of particle physics, and the honest answer is that no one knows for certain. There are possibilities, and each one points beyond the Standard Model into physics we have not yet confirmed. One possibility is that right-handed neutrinos do exist, but are extraordinarily heavy, far too heavy for any machine we have built to produce, and that through an elegant piece of mathematics called the seesaw mechanism, their enormous mass forces, the ordinary neutrinos we see to be incredibly light. The heavier the hidden partner, the lighter the visible neutrino, like a seesaw, push one end far down and the other rises high. This would neatly explain why neutrino masses are so absurdly tiny compared to everything else. Another possibility is stranger still, that the neutrino is its own antiparticle, a kind of particle that physicist Ettore Majorana imagined back in 1937, which could acquire mass through a completely different route that requires no right-handed partner at all. Experiments around the world are hunting for a rare process called neutrinoless double beta decay, which would only be possible if neutrinos are their own antiparticles. So far, no one has ever seen it, but the search goes on with ever more sensitive detectors, because finding it would reveal an entirely new kind of mass, generated by physics we do not yet understand. There is a quiet wonder in just how much these ghostly particles had to teach us before we even knew they carried weight. For decades, the slight shortfall of neutrinos arriving from the Sun was treated as a nuisance, a possible error in the experiments or in our model of how the Sun burns. Detectors kept finding only about a third of the electron neutrinos that the Sun's nuclear furnace should have been producing. Theorists checked the solar models. Experimentalists checked the detectors. The numbers stubbornly refused to add up, and for a long time, nobody could say why. The resolution, when it finally came, was not that the neutrinos were missing, but that they had been changing their identity in transit, arriving as flavors the early detectors were blind to. The Sun was producing exactly as many neutrinos as predicted. We had simply been counting only one kind and missing the others, like standing at the end of a road counting red cars and concluding that 2/3 of the traffic had vanished, when in truth, the cars had only changed color along the way. That single insight, that neutrinos shift flavor as they fly, resolved a mystery that had nagged at physics for a generation, and in doing so, it proved that neutrinos have mass. And the implications ripple outward in ways that touch the largest structures in the cosmos. Neutrinos are the second most abundant particle in the universe, after the particles of light themselves. They are everywhere, flooding all of space, left over in vast numbers from the first second of creation. Because there are so many of them, even their tiny individual masses add up to a real gravitational influence on the universe as a whole. If neutrinos were significantly heavier, their combined gravity in the early cosmos would have smoothed out the slight ripples in the density of matter, the very ripples that later grew into galaxies and clusters of galaxies. The web of structure we see across the sky, the great filaments and walls and voids, is sensitive to the total mass of all the neutrinos in existence. Astronomers studying the largest patterns in the universe can therefore place limits on something as intimate as the mass of a single neutrino, tying the very small to the very large in one elegant thread. The mass of the lightest, most elusive particle in nature is written faintly into the architecture of the entire cosmos. And whatever mechanism gives neutrinos their mass, whether it is a hidden heavy partner working through the seesaw, or the strange possibility that the neutrino is its own antiparticle, that mechanism is a piece of physics beyond everything in the standard model, hiding inside particles that pass through you, unnoticed, 100 trillion times a second. And there is a final strangeness. We do not even know what the neutrino masses actually are. Oscillation experiments only reveal the differences between the masses of the three types, not the masses themselves. We know those differences are tiny, which tells us neutrinos are at least 1,000,000 times lighter than the electron, the next lightest particle. But whatever mechanism gives them their mass must also explain why that mass is so impossibly small compared to everything else in the universe. The neutrino mass is not a footnote. It is a signpost, a clear and undeniable marker pointing toward physics beyond the standard model. The most successful theory ever built cannot, in its original form, account for the mass of the most abundant matter particle in the cosmos. And those massless seeming ghosts, 100 trillion of them sailing through your body every second, each one carries a tiny weight that our best theory of matter cannot explain. Proof that our understanding is incomplete is, quite literally, passing through you right now in unimaginable numbers without a sound. Part 11. Borrowed ground. There is one more unsettling thing about the Higgs sector, and it concerns not the masses of other particles, but the stability of the field itself, the very ground the universe stands on. Precision measurements of the Higgs boson's mass and the top quark's mass, taken together, suggest something quietly alarming. The Higgs potential, the energy landscape that determines how the Higgs field behaves, may not be perfectly stable. The universe might be sitting in what physicists call a metastable vacuum. To understand what that means, picture a ball resting in a shallow valley partway up a hillside. The ball is stable in an ordinary sense. Give it a small push and it rolls back and settles where it was. It is not going anywhere on its own, but it is not at the lowest point in the entire landscape either. Further down the hill, beyond a ridge, there is a deeper valley, a more stable place. The ball could rest, if only it could get there. The ball is stable, but only locally. It sits in a comfortable dip that is not actually the bottom. Current measurements suggest the universe might be in exactly this situation. The Higgs field sits at a particular value, resting in a particular valley of its potential, but there may be a deeper valley at much higher field values, a truly stable configuration that the universe has not reached. The calculations place a potential instability somewhere around 10 to the 11th power giga-electron volts, and remarkably, our universe appears to sit right at the knife's edge, extraordinarily close to the boundary between a stable vacuum and an unstable one. If the vacuum is indeed metastable, then in principle, something extraordinary could happen. Through quantum tunneling, the same quantum strangeness that lets particles slip through barriers they should not be able to cross, a tiny bubble of the deeper, truer vacuum could spontaneously form somewhere in the universe. Inside that bubble, the Higgs field would sit at its deeper value, and the laws of physics would be different. Particle masses would change. The delicate balances that allow atoms to exist might no longer hold, and the bubble would expand outward at nearly the speed of light, its walls sweeping through space, converting everything it touched into the new vacuum state. You would never see it coming. Because the bubble wall travels at nearly light speed, it would arrive at the same instant as any warning of it could. There would be no signal, no flash, no time to react. Everything within the bubble, matter, energy, all the structures we know, would simply be rewritten. Now, before this keeps you awake, let me be very clear about the timescales, because they are reassuring in the extreme. This scenario is speculative, and it depends on physics at energies far beyond anything we can currently measure. And even taking it seriously, the calculations say that if our vacuum is metastable, its lifetime is vastly, almost incomprehensibly longer than the current age of the universe. The cosmos has existed for about 13.8 billion years, and a metastable vacuum of this kind would be expected to last enormously longer than that before any such bubble appeared. There is no practical danger here, nothing to fear in any human or even cosmic time frame. Moreover, the conclusion rests on the precise values of the Higgs and top quark masses, and small shifts in those numbers can change the answer entirely. If there is new physics waiting at higher energies, new particles or forces we have not yet found, they could stabilize the vacuum completely. Many physicists, in fact, expect exactly this, precisely because a metastable universe feels like an unsatisfying final state of affairs. But notice what this possibility means, even setting fear aside. The Higgs sector, the part of the Standard Model that was supposed to explain mass and make the universe possible, might itself be only temporarily stable. The very mechanism that grants particles their mass and allows atoms and stars and people to exist might be a local minimum rather than the true bottom of the landscape, a comfortable valley that is not actually the deepest one. The universe might, in a sense, be living on borrowed ground, resting in a configuration that is stable enough to outlast everything we will ever know, yet possibly not the final word. The pencil we balanced earlier on its tip, the improbably fine-tuned Higgs mass, returns here in a larger and stranger form. It is not just one number that seems impossibly balanced. It may be the entire foundation of mass, standing upright far longer than the universe has existed, and yet perhaps not standing forever. This is not the picture of a finished, closed story. It is the picture of a theory that raises as many questions as it answers, and it is why physicists are now looking outward, toward bigger machines and deeper experiments, hoping to find the new physics that would resolve all of this. There are ideas about where the answers might lie. Grand unified theories try to merge the three forces of the Standard Model into a single force at enormous energies, placing quarks and the lighter particles into shared mathematical structures that could finally relate their masses to one another. Some versions predict that the proton itself, the seemingly eternal building block of all matter, very slowly decays, though decades of searching in vast underground detectors have never caught a proton in the act. Other physicists look to extra dimensions of space, hidden and curled up too small to see, in which the different generations of particles would be different vibration patterns, their masses set by the geometry of those hidden dimensions. And string theory, the most ambitious framework of all, imagines every particle as a tiny vibrating string, its mass determined by how it vibrates within a hidden geometry, dreaming of a single shape from which every mass and every force would flow, though it faces its own staggering problem of a near infinite number of possible shapes with no known rule to select ours. It is worth dwelling on just how close to the edge our universe appears to sit, because the precision of it is part of what makes physicists uneasy. When you plot out the stability of the Higgs potential, as it depends on the measured masses of the Higgs boson and the top quark, our universe lands almost exactly on the line that separates a fully stable vacuum from an unstable one, not comfortably inside the stable region, where there would be nothing to discuss, not deep in the unstable region, where the universe could not have lasted. Right on the boundary, in a narrow strip physicists call metastability, where the vacuum is stable enough to endure for vast stretches of time, but is not, technically, the lowest possible state. This knife's edge placement could be a coincidence. Or it could be a clue, a hint that the values of the Higgs and top masses are not random at all, but attuned by some deeper principle we have not yet uncovered, a principle that likes to leave the universe balanced precisely at the edge of stability for reasons of its own. We do not know which it is, and that uncertainty is itself a kind of signpost, pointing toward physics we have not yet found. And this is really the thread that ties the entire night together. Every mystery we have walked through tonight, the unexplained pattern of particle masses, the proton's weight conjured from energy, the impossible lightness of the Higgs, the missing supersymmetry, the neutrinos that should be massless and are not, the vacuum balanced at the edge of stability, every one of them points in the same direction. They all whisper the same thing. The standard model, magnificent as it is not the final word. It is a map that guides you flawlessly through the territory we have explored, and then, at its edges, dissolves into regions marked only with question marks. The hierarchy problem is one such edge. The flavor puzzle is another. The neutrino masses are another. The vacuum stability is another. They are not scattered, unrelated flaws. They are a constellation, and a constellation has a shape. Physicists look at that shape and feel certain that something deeper is hiding behind it, some larger theory in which these separate mysteries would be revealed as different views of a single underlying truth, the way Newton revealed the falling apple and the orbiting moon as one. We have not found that theory yet, but the very fact that the mysteries cluster, that they point the same way, is reason to believe it is out there, waiting in the dark beyond the edge of the map. To test these ideas, physicists are planning and building the next generation of machines. An upgraded version of the Large Hadron Collider, with far greater intensity, will begin running in the coming years, and will study the Higgs boson with much greater precision, measuring exactly how it couples to other particles, watching for the smallest deviation from the standard model that would betray the presence of new physics. Beyond it, there are proposals for enormous new colliders, machines that would collide electrons and their antimatter twins in conditions so clean they could measure the Higgs boson's properties to better than 1%, where even a tiny discrepancy would point the way forward. Neutrino experiments are firing beams of neutrinos hundreds of kilometers through the Earth to pin down the ordering of their masses, while other detectors hunt patiently for that rare decay that would reveal whether the neutrino is its own antiparticle. Every one of these efforts is a bet, a wager that the unexplained numbers of mass are not meaningless accidents, but messages, signposts pointing toward a deeper layer of reality we have not yet reached. The mystery is not a dead end, it is an invitation. Part 12. 3 masses, 1 face, and an open door. Let me draw all of this together now, slowly, because the picture that has emerged over the last couple of hours is genuinely strange, and it deserves to be seen whole. When the world heard that the Higgs boson had been discovered, the natural interpretation was that the mystery of mass had been solved. The headlines encouraged that belief, and the achievement was real enough to make it sound true. But the reality, as we have walked through it, is far more nuanced and far more interesting. One of the most surprising things we have uncovered tonight is that mass is not a single phenomenon at all. It is not one thing with one explanation. It is several different phenomena, generated by different mechanisms, operating at different scales, governed by different physics, and no single theory explains all of them together. Consider the three layers we have descended through. The first layer is the fundamental particles, the quarks and electrons and their heavier cousins, the W and Z bosons. These acquire their mass through the Higgs mechanism, through their interaction with the Higgs field that fills all of space. This is real, this is confirmed, and the discovery in 2012 proved the field exists. But while we understand the process completely, we have no idea why it produces the particular values it does. The interaction strengths are free parameters, measured and not derived, and nobody knows why the electron is as light as it is or the top quark as heavy. The second layer is the composite particles, the protons and neutrons that make up almost all the mass you can touch. These get the overwhelming majority of their mass not from the Higgs field, but from the energy of the strong force binding their quarks together, energy converted into weight through the equivalence of energy and mass. Less than 2% of a proton comes from the Higgs. The third layer is the neutrinos, those ghostly particles whose masses the original Standard Model flatly forbids, whose weight requires entirely new physics that we have not yet identified. 3 layers, 3 different origins of mass, 3 separate stories that happen to produce the same single property. The resistance to being pushed, the pull toward the ground, and these layers are tangled together. The quark masses that feed into the calculation of the proton's mass come from the Higgs field, which leaves them unexplained. The Higgs field's value is set by the Higgs potential, whose shape is unexplained. The Higgs boson's own mass raises the hierarchy problem, with its impossible fine-tuning and its missing supersymmetry, and the neutrino masses point past everything we currently know. Pull on any single thread, and you find it connected to all the others, the whole tangle resisting every attempt to comb it straight. The Standard Model, for all its breathtaking success, carries roughly 26 numbers that it cannot predict, that must be measured and inserted by hand, and the great majority of them are tangled up with mass and the Higgs sector. We have a theory that describes the behavior of fundamental particles with a precision unmatched in the history of science, a theory that has never once been contradicted by experiment, and more than half of what we feed into it is just numbers we copied down from nature without understanding where they come from. It is a recipe that produces a perfect result every time, with a list of ingredients whose quantities are all marked with question marks. There is something philosophically striking about where this leaves us, and I want to end there because it changes how the whole story feels. For centuries, physics advanced by unification. Newton showed that the force pulling an apple from a tree and the force holding the moon in its orbit were one and the same. Maxwell showed that electricity and magnetism were 2 aspects of a single field. Einstein wove space and time together into one fabric. The Standard Model itself joined electromagnetism and the weak force into one. Each great step replaced 2 mysteries with one deeper understanding. The history of physics is a history of things turning out to be the same thing. But mass resists this pattern. Instead of converging toward a single explanation, mass seems to fracture into more phenomena the closer you look. Fundamental masses come from one source, composite masses from another, neutrino masses from a third, and the values of all of them remain unexplained. The deeper you dig, the more questions you find. This might mean we simply have not yet found the right unifying framework, that somewhere out there is a single principle from which the Higgs potential, the strong force energy, the neutrino mechanism, and every particle mass all flow, waiting to be discovered. Or it might mean that mass is genuinely composite, not in the sense that particles are made of smaller parts, but in the sense that the word mass is an umbrella covering several distinct phenomena that happen to wear the same face. Either answer would be profound, and either remains possible tonight. And here is the thing worth holding on to as you drift. The universe cares about these unexplained numbers more than almost anything else. The masses of the particles are not trivial details. They are the blueprint of a reality that permits complexity in chemistry and life. The proton is just slightly lighter than the neutron by about 1 part in 700, and that tiny difference is why protons are stable, why hydrogen exists, why stars have fuel to burn. Shift the masses of the lightest quarks by a hair and protons might decay, atoms might never form, and the universe would be a lifeless wash of radiation. Make the electron much heavier, and atoms would shrink, and chemistry would change beyond recognition, and the molecules that life depends on could not hold together. The specific values of these masses, the very numbers no theory can explain, are tuned in a way that allows you to exist, to hold an object in your hand, to feel its weight, to wonder where that weight comes from. Think for a moment about what a satisfying answer would even look like, because that question turns out to be surprisingly deep. When physicists say they want to explain the masses of the particles, what kind of explanation would actually content them? One possibility is what they call a calculable theory, a deeper framework that takes in fewer numbers than the standard model and produces all the masses as outputs rather than inputs. In such a theory, you would feed in a small handful of fundamental quantities, turn the mathematical crank, and out would come the mass of the electron, the mass of the top quark, the masses of the neutrinos, all predicted, all derived, none of them simply copied down from nature. That would be the most satisfying outcome imaginable, because you would understand not only how mass arises, but why it takes the precise values it does. The mysterious numbers would stop being mysteries and become consequences. This is the dream that animates grand unified theories and string theory alike, the hope that beneath the apparent arbitrariness lies a hidden order from which everything follows. Another possibility, harder to swallow, is that the values are simply environmental, that they vary across a vast landscape of possible universes, and that we observe ours not because any equation demands these particular numbers, but because only universes with numbers close to ours can contain observers to do the observing. And a third possibility, more subtle than either, is that the masses are fixed by some mathematical structure we simply have not recognized yet, a pattern hiding in plain sight, a symmetry or a geometry or a relationship that no one has stumbled upon, so that one day someone will find the right framework and the masses will suddenly click into place like a combination lock springing open, and we will wonder how we ever failed to see it. The honest truth, the answer most physicists would give, if you press them late at night, is that we do not yet know which of these is correct. We do not know whether the masses will be calculated, or selected, or revealed by a hidden pattern, or understood through some approach no one has yet dreamed of. That uncertainty is humbling. It is also thrilling, because it means the deepest chapter of this story has not been written, and the people who will write it may be alive right now, may even be listening to something like this, drifting towards sleep with the strange thought that the weight of their own body is a clue to a mystery no one on earth has solved. There is one more image I want to leave you with before we let the night close, and it returns us to where physics has always found its greatest triumphs. Every major step forward in the history of science came from an incomplete explanation that pointed beyond itself. Newton explained the motions of the planets with breathtaking accuracy, and yet he could not explain why gravity worked the way it did, what it actually was. That gap, that honest admission of something missing, was eventually filled by Einstein, who revealed gravity as the curvature of space and time itself, a far deeper truth than Newton could have imagined. The Standard Model is in exactly that position now. It explains how mass arises with extraordinary precision, and it cannot explain why mass takes the values it does. That gap is not an embarrassment. It is a doorway, the same kind of doorway that has led, again and again, to revolutions in our understanding. Whatever lies on the other side of it will deepen our picture of mass, of particles, of the very structure of reality, in ways we cannot yet foresee. The incompleteness is not the end of the story. It is the promise of the next chapter. So return, one last time, to the weight in your hand, the object you picked up at the very beginning, that you may still be holding, or that you set down hours ago. That simple downward pull, the most ordinary sensation in the world, the thing you have felt every second of your life without once thinking about it. You now know that almost none of that weight comes from the Higgs field that the headlines celebrated. You know that nearly all of it is the bottled energy of a storm raging inside particles, too small to ever see, motion and force frozen into the appearance of solid substance. You know that the particle the world was told had solved the mystery of mass, instead opened a door, and that on the other side of that door waited 3 deeper mysteries and a number so finely balanced it looks like the universe holding its breath. The discovery of the Higgs boson did not complete the picture of mass. It confirmed that the story is real, that the questions are the right questions, and that the answers are still out there somewhere, waiting to be found. Every proton in your body carries weight the Higgs field barely touches. Every neutrino passing through you right now carries a mass our best theory cannot explain. The Higgs boson sits at 125 giga-electron volts, a value that seems to demand either a miracle or a mechanism we have not yet discovered. Mass is the property that makes matter feel real, the reason the universe has structure instead of being a featureless rush of weightless light. And it remains, after all our progress, after the greatest machine we ever built and the half-century search that found exactly what it was looking for, one of the deepest and most beautiful unsolved puzzles in all of nature. The Higgs boson gave us one piece of the answer. The rest is still out there, in the dark, waiting, and that door is still open.